What the hell is that's a lot of Internet Explorer open, which is more Internet Explorer than you ever want to be open. I like Edge. I find Chrome to me is slow. It's nice. It's got all the great additions, which are nice, but I find it painfully slow.
And then I drop.
Okay. So let's start today. Last year I had them start with. Oh, I don't want to delete that. Sorry, 1 second. I can't multitask. I can't even unitask. I just can't task. Last class I had them start by answering kind of a little problem challenge. You can do that if you want, or I can just take up some homework, which might be more apropos. I had them do that because I don't want to use for a minute, but.
Let's start that. Oh no, never mind. I haven't done that yet.
So, any questions from yesterday's homework? Questions that gave people trouble? Everyone's a rock star. Everyone's totally got it. Everyone's like, yes, I'm brilliant. I know this. Everyone's like, Orlando, drop dead. I'm not doing your homework no matter how sarcastic you get in front of the room. Like, you know what? We all right? I don't remember that. Did I give him hell? That'd be Ahmed. What did I say? Not yet. Give it some time. I've been eating a lot. Anyway, the class that like you complain about the work every day that you don't like it, and it's yeah. It's like a comedy mirrors. You never know. It's like a train wreck. You can't look away. Anyway, nothing from the homework. Then I'm going to have you do the little challenge question here. I'm going to give you 5 minutes. But I want you to imagine this. Same reaction we looked at yesterday. Same reaction. Here we have methane reacting with oxygen to make CO2 and water. It's got a delta H of what?
Negative 2.5 times 10 to the second kilojoules.
Yeah, so negative 250 kilojoules. Right, so 250 kilojoules. Same reaction we talked about yesterday. Negative, so that is
Exothermic.
Meaning
It
gives off energy in the form of heat. Okay, this is giving off heat. So this is what I want you to imagine. I want you to imagine that we're working in a little industrial setup, and for whatever reason, can't imagine why we would be doing this, but we are burning methane and collecting the CO2 it produces. All right? Maybe we run labs that do different things that need heat, so we use methane as a heat source, which is pretty common. But then we also sell compressed gas cylinders of CO2. So a real quick way to fill those up is just to collect the gas off the reaction chamber, which, by the way, they do. Right? If you're gonna run a reaction that requires pressure, why not use it to do something, right? So they're doing this. So they're filling cylinders. I want you to imagine that 100-liter gas cylinder, the big industrial thing. They keep it at 25 degrees Celsius. It has a maximum safe pressure of 10,000 kilopascals. What I want to know is, if they observe 3.5 times 10 to the 4 kilojoules of energy released, is that safe? Will it stay in the cylinder? Or will this cause the safety valve in the cylinder to have to open? Is this going to exceed 10,000 kilopascals? That's the challenge. Right? Get to it. Hi, Alex.
Where's you go?
Oh, and maybe we'll erase the answer on the right, because I meant to do that earlier.
You could just slide the board over, and you wouldn't have to rewrite it.
I like writing. That makes me feel.
Apparently, Alex sent us a fax. Who still faxes things? I don't know.
Oh,
I know those.
guess what? Do you know that? So the DSP, I do home instruction, and I got a note the other week saying, as of February whatever, you will no longer be able to digitally submit your timesheets. You must fax them to the board office. And I thought, what ridiculous world are we living in? For 2016, we're getting a note that says you have to stop using a Google Doc so we can send a fax.
Do you even have a fax
Honestly,
machine?
I don't even understand.
Or when it
It's
was
like we mentioned the bizarro. Down. And please fax me your time sheets anyway. No. But we're talking here, so this can be collaborative. Cool. Cool.
25 degrees Celsius, which equals
What the hell?
200.
What did you do here? What is this and how did you get
Why not
82
one
times 2?
Yeah, because it's 2 moles.
That's
Is it 2 moles or is it 1 mole? No, this.
Why wouldn't you just do it for 1
Oh,
mole?
Alex, like, has like white signs that
Why do you have 2 moles? Why do you just?
Because up here, the reaction gives you 2 moles of oxygen.
Somebody isn't out.
Yes, but why did you put 2 here? This has to be 1.
Nope. Because that's how many moles you get for that much energy. It gives that much energy. That many moles.
This has to be negative.
Nope. They do not matter. Okay, so that's that much Kelvin. Okay, so moles. So we get. Okay, so CO2, you get 1 CO2.
Oh, God, look at this. Just enough. Yeah,
It charges through USB.
Yeah, which is nice.
That's kind of,
That's a plus. Because you can charge it in the car.
that's,
So I don't have a calculator.
I do.
Oh, I got Steven.
Oh.
PV equals.
Okay. By the way, guys, if you don't remember R, it's 8.314 liters kilopascals per Kelvin. I was sitting in the lunchroom yesterday, and I said out loud to myself, "What's the capacity of water again?" And Ms. Green from across the room, who was eating pasta and carrying on a completely different conversation with somebody, said 4,186 joules per. It's just instantaneous. Oh yeah, that's so that means your physics at university. Carbon is 12, oxygen is 16, so 32.
Oh, wait, sorry. Fine.
No. Oh, so it has a maximum.
That's me, definitely me. I recognize my notes anyway.
Say.
You're damn good.
Wait, what's this?
Well, looks good.
What's this? This is just solving.
Take back Kelvin.
Yeah.
No, it's all.
That's so dismissive. I mean, you said. But it still looks nice. Yeah, it looks great.
Looks nice, it's annoying.
Still looks awesome.
Aww, there's annoying and useless.
Just sometimes. I told you my zombie about it, right? Like just that in the end, if there was some kind of apocalyptic event and the world was left, I have no skills.
You have chemistry.
Yeah, that's what I don't know practical chemistry, so if I can tell people like roll the mass of CO2 incorrectly. Wait, is that self-correct relative? I can't. No, I would be good, and I assume I'm delicious. I would be good so quick. Yeah. Yeah, I haven't watched The Walking Dead yet, but I would be like, whoever like the guy in the first episode, where you're like, that's kind of a funny character. Oh, he's dead. That'd be first episode. God.
Gonzo.
I'm a red shirt.
Oh, she's useful. Oh, she's like the main of the poster. And maybe she'd keep me around, but like if she's being practical, I can't blame her. She should find somebody who can build something. And I get that. Like all bets are off. It's post-apocalypse. Richard Ferrero sickness, health, nothing about zombies.
Man,
Nothing. I don't blame her.
I got this all for itself.
No, you don't have to be the fastest.
And I'm faster than both the people.
You don't have to be fastest, you just have to be not slowest.
Why do you have to be so?
I know.
No,
Okay, that's it.
Your lack of energy because you don't eat food.
man, Connor Rosie's got it made though, because we're in a death trap here
Oh, well, I didn't see that happen.
at the school. Have you not seen Walking Dead? They go to school, and everybody's down there.
We can just live in the courtyard.
So Connor Rosie's got it made because he doesn't go to school.
Okay. You raise a good point. I was gonna make a zombie joke, but I was gonna stop. That's what I'm gonna do. I'm just gonna not go down the rabbit hole.
So what is
Yeah.
8.314 kilopascals per liter per kilopascal liters per kilojoule? What is that? What are you pointing at? The R value?
That's the R value.
There you go.
Oh, yes, definitely.
Well, you tell me, which one's good, which one's bad?
Well, it's gonna be more right than whatever I come up with, so.
Yeah.
Is that kilojoules?
Yeah.
No, this here.
What?
I don't know.
No, it doesn't matter. No, it doesn't matter.
No, and it doesn't.
He's just asking.
You don't need to use a
Right,
math anyway.
All right.
You can work on it, right? The PV equals NRT, nothing but math. And I didn't give you a math.
Yeah, kilojoules.
No math.
Where'd you get that number?
So we need to know how many moles. But what did I give you? I didn't give you a mass, I gave you up here. So we need to just like with the energy because you're still right in a one mole reaction. How much energy do I get? 2.5 times
It's just asking on CO2.
right? But how many did I actually get? That. So then you just stoichiometry with that number. All right, so do you want a minute? Okay, take a minute. Take them.
We get these faxes at least once a day.
Okay, let's focus. You have the answer?
No, I have no idea what's going on.
Whoa.
Sorry.
Whoa.
Did I do it wrong now?
No, I-
What's one?
It's a fax.
The stamps.
We want to get to buy video.
We only take that every time because we don't have to.
I did do it right.
Fuck you both.
You know it's true.
Okay, if you're still going, keep going. If you've given up, pay attention here. Or if you're done, pay attention here. We're just gonna start it up here. What equation are we using? P. Okay. Heat equals RT, pressure times volume equals number of moles times the ideal gas constant times temperature. What are we solving for? Pressure. So how do I rearrange this? P equals nRT over V. Okay, so let's go through here. Do I know N?
No.
That's a bad start. Okay, do I know R?
Yes.
What is it? 8.314 what?
Liters times kilopascals over Kelvin.
Good. All right, and T.
You have to convert it to Kelvin.
Okay, so what is it?
It is
290.
98 Kelvin.
Okay, and you're right, but I'm just gonna go with 3 sig figs because that's more than I need. I think. Yeah, we're good. Okay, and then V,
100
100 what?
liters.
All right, are all those units right?
Yes.
Okay, So the only thing I need to know is N. Okay. I need to know how many moles of CO2 there are. Okay, that's great. So I just need to take the mass and use the molar mass, right? Nope. I'll just take the mass from the question. Oh, why not? That's what I wanted. I wasn't given a mass, but I was given energy. Okay. How much energy was produced by this reaction?
35,000.
35,000 kilojoules. Okay. If it had been 1 mole of CO2 made, how much energy would have been released?
250.
Okay, so obviously it's more than 1. Is it 10 moles? Like, it's more than 10. Okay, so just to give us a sense of where we should be at, right? We're talking lots of moles, right? It should be more than 100, shouldn't it? Right, okay. So, we're going to have to do some stoichiometry. For stoichiometry, the first thing I write down is always my given, right? What's my given?
35,000 kilojoules.
Okay. 2.5 times 10 to the 4 kilojoules. Now, I don't want kilojoules, so what am I going to do? I'm going to put kilojoules on the bottom, and on top, I'm going to put moles. Moles. Where do I find the ratio of moles of CO2 to kilojoules? Okay, how many moles of CO2 in the equation? 1. How many kilojoules?
2.5.
Okay. By the way, I'm not putting the sign because the sign tells me the direction, right? Do I care about that for the purpose of this equation? All right, what do I get? 140
Moles of CO2.
moles. Okay, now what do I do? Oh. Okay, what do I do with that number? All right. And when we do that, what do we get?
I know we're bunny with the line.
When we do that, what do we get? 3,470. Okay. And of course, how many sig figs should we have? 2. By the way, if your inclination is to say, what about that 100 liters? Since that's a cylinder that we bought from like a company, I'm going to assume that they have at least 2 sig figs there, right? Like if you buy a 100-liter gas cylinder, it's probably not 52 liters, right? We trust it to be in the ballpark. Yeah.
Why are you doing sig figs if that doesn't matter?
That's a good question.
Because it just doesn't.
It's a good habit of mine. Why do we wash our hands after we go to the bathroom? It's not because the act of going to the bathroom actually gets much bacteria on you. Urine's sterile. It's a good habit of mind. It reminds us to frequently wash our hands. Also, the bathroom itself is probably filthy from other people, but no less so than that door handle, which, by God, just thinking about it is horrific. The things on that door handle. So, habits of mind. You can think of sig figs like washing your hands after going to the bathroom. It's just something you should do, and when people don't, you should judge them. All right? When you go somewhere and somebody doesn't wash their hands at the bathroom, you should think, I'm not sitting down at the cafeteria table with you. That's what I'm not doing, because I like my hygiene. Anyway, moving on.
Why don't we have graphs going?
I don't know. Moving on. Go. Yeah. Oh, hey, it totally would. So I washed my hands in the bathroom, but I didn't do a very good job. I didn't use a whole lot of soap. I didn't do the whole 2 happy birthdays thing. Okay. That's what you tell little kids, that they have to be able to sing happy birthday twice for the amount of time they should wash their hands. Whatever. Okay. Point being, and then they go, happy birthday to you, happy birthday to you, happy birthday to you, happy birthday to you. It just tells them they should do a good job washing their hands. You'll pick up some of these tricks when you become a parent one day, if you become a parent one day. There you go. Okay. Yeah. No problem. It comes from 25 degrees Celsius, and to convert Celsius to Kelvin, we just add 273.15. And that's just always the same. So to go from Celsius to Kelvin, you add 273.15.
So why isn't it 298.1?
Because sig figs. Right? My Celsius is when you add, you go to the lowest number of decimal places. And in this case, that's no decimals.
Okay.
Yep.
So what
Yep.
Why can you just say 28 Celsius?
That's a great question. The reason is a difference of Celsius and Kelvin is identical. I'll tell you why. if you added 293 to the first number, and then also add 293 to the second number, and then subtract them out, that 293 ends up just, and I'll show you what I mean. Say we were finding the difference between 5 degrees Celsius and 0 degrees Celsius. And I want to do it in Kelvin. This would become 273 plus 5 minus 273 plus 0. Right? Does that make sense? Okay. Now we're going to use the distributive property. Math skills. Zombie apocalypse, dinner. 273 plus 5 minus 273 minus 0. The 273s cancel each other out. So it's still just 5. Will you get the right answer if you convert them to Kelvin? 100%. Is it a complete waste of time to do so? 100%. But you won't be wrong if you do. What you can't do is find the difference and then add 273. That would be wrong, right? The difference is not 278, right? You would have, if you're going to do it, you have to change both numbers before you do any math. In the case of finding a delta t, it doesn't make a difference. Whereas in the case of t, it obviously makes a difference. If it's one of those habit of mind things where you want to go, you know what, every time I see a Celsius, I want to make it Kelvin so I don't screw it because I don't know when to and when not to, then go ahead. But just make sure you don't do it at the end. You do it at the beginning to both temperatures. Okay, so does our cylinder burst? Good. I like this kind of question on it. Okay, so my surprise is only but Ms. Burns came and watched my class. Hi, Ms. Burns, by the way. She's watching 2 of my classes today, I'm sure. Because she watches this one every day, as we all know. Okay. So you've already ruined my big demo. What else? What else? Okay, so my big demo was, so I thought that originally my plan was challenge Grace Tennant to a race in first period. And then so I was gonna say, okay, this is the setup. We all went outside and said, okay, we're gonna say just race, simple rules, like whoever covers the most distance in the least amount of time wins. So the distance, we're both gonna do the same thing. Run to the end of the hall and come back. So fastest time to complete that wins. And then I was gonna say go, then I was gonna pull a donut out of my back pocket and eat it while she ran. And then when she came back, I was gonna declare myself the winner. We'll talk about why in a minute. So then I thought, oh, Miss Burns is coming to my class day. It was my time to be observed. So I thought, this is perfect. I'll challenge Miss Burns to a race. Then I thought I could do one better and have Miss Burns think she was going to have to race Grace, which I think stressed her out a lot. But I had Grace do the same thing, minus the donut. I ate the donut. Complete disclosure. That actually wasn't a donut. That was just a joke. I was going to get a donut, and then when I decided I was going to have a race Grace, I didn't even buy a donut because I knew I would eat the donut. And I don't need so instead I ate the yogurt. Really better. So, you know, it was a funny moment, whatever. But it reminds me of something that you talked about in physics, right? One of these pedantic little points where they go, who's gone more distance? The person who ran down the hall and ran back. And of course, if we treat distance as a scalar, in the first case, Ms. Burns went, say, positive 20 meters. Then she turned around and she went negative 20 meters. And so her total displacement is 0 meters. So me, by simply not moving, or Grace as my surrogate, won the race because she also moved 0 meters, but she accomplished that sooner. Stupid little joke. What's that got to do with chemistry? Hess's law, yeah. What the hell does that mean? So let's talk about it. Someone have this out for me, please? Okay.
They talk about that on Caribbean.
So Hess is kind of the jokester of the chemistry world, but he plays like the jokes on chemistry itself. All right, so I start this with a little quote. There's an ancient Chinese proverb that says, there are many ways to climb a mountain, but the view from the top is always the same. There you go. That's one of the ways. I like the idea of like the Google Street View. I'd like to just be able to drop that little guy on there and just like 360 panorama, eating the donut. Eating the donut, panning the camera, good enough for me. I'll open a window if I want to be chilly, like it would be up there. So I have the setup here, but not unlike epic races. Oh yeah, at one point I was going to eat a sub. I thought that would have been even funnier if I could try to eat an entire sub in the time it took her to get done. And I thought that would just be revolting. Nobody wants to see that. But it became, in my mind, a little challenge to myself. Could I? And I still think I probably could have. Anyway, shouldn't go that fast. Anyway, not unlike epic races with me, if a series of chemical reactions start and end in the same places, they'll have the same delta H. And it doesn't matter whatever path you take. In other words, if I go from here to there, that's what, 3 meters? I will have traveled a distance of 3 meters. If I walk up and down the room and around and through all the rows and out down the hall, get in my car, go to Tim Hortons, buy a coffee, come back, decide that even though I didn't get a donut, it's what I really wanted, get back in the car, go back to Tim's, get the donut, come back, walk down the hall, come in, stand there, eat the donut. I've still really, when all is said and done and measured it, I've gone 3 meters. Obviously, my cumulative distance is greater, but the displacement, the change in position is the same. That makes sense? Okay. Chemical reactions work in the same way. If I start with a set of products and end with a set of products, I will get a certain delta H. And it doesn't matter what I do in the middle. I can do some reactions that produce tons of energy and follow them up with some reactions that absorb tons of energy. But whatever steps I do in the middle, if I start with products and end with products, I'll get a certain delta H. And whatever sequence of reactions I use to make that happen is an irrelevance. So I was thinking that this chemistry thing, this chemistry teacher thing, oh, I like it, it's good. But yeah, I get paid pretty well. I get paid better. So I thought I should start using my chemistry skills to make something. Something that people would spend money for on a black market, maybe. You know, like a kind of product that maybe like people want, and like those people out there who make like a high grade version of it, but like those people who control that, and it's very expensive, and you have to go to like a supplier and get it. But there's got to be a market for a product like that was made by like me in my basement, and they'd pay me money. So I'm gonna make diamonds. Yeah. I think, well, no. Can I just say, if you watch that show and your takeaway is meth was a really good thing for Walter White, I'm going to suggest you missed the point. Just my own 2 cents. He didn't get caught. He got. Okay. He's kind of at the point that, yeah, like, you know, he's going to die from the first episode, right? Anyway. So I want to make diamonds. How do we make diamonds? Good. We're going to take pure carbon. What do we call pure carbon? Graphite. Yeah. Now, we're going to take some graphite. And I want to make it into, and I'm going to make it into a diamond. This is my brilliant scheme. It's a bracket. It's a bracket. Okay, so I'm going to make graphite into diamond. Diamond's expensive. I can make mad cash or like a carbon. I can burn something. But diamonds I can sell. It's great. Okay, so here's the problem. I did a little bit of research, and we can make diamonds under laboratory conditions. We take some carbon, and we have to give it lots of heat and lots of pressure. Now, by the way, the fact that we have to do that doesn't mean necessarily that it's exothermic or endothermic. It doesn't tell us anything. We know that we have to do that to start the reaction. For example, if you want to burn gasoline, you have to provide heat. But in the end of the reaction is exothermic. So we don't know. I don't know if this is exothermic or endothermic. I want to do a bit of research. I want to know what's the energy requirement when all is said and done for this. Now here's the problem. So I'm going to put it in the calorimeter. Reaction to the temperature change. So I'm all ready. I set it up. I got my carbon. I'm good to go. I did a little bit of research. And one of the ways they make diamonds industrially is they take carbon and they surround it with high explosives, because that provides a lot of heat and energy really quickly and pressure. And then they dissolve it in boiling concentrated nitric acid and leave it there for 3 days. And I got thinking, I've hurt myself cooking dinner many times. I don't know that this is the reaction for me. So I decided not to do it. I'm out. I'm out of the international diamond smuggling ring as soon as I'm in. It's just not for me. Too much pressure. Back to
Literally.
yeah, not even a pun, just yeah, what it is. So I'm back here. But I'm still kind of curious about the delta H of this reaction. Now again, I said I'm not going to sit here in the lab and turn graphite into diamonds. But could I take some carbon and burn it?
Yeah.
Yeah. So what would that reaction look like? I could take some graphite. And I could burn it. What's a reaction that burns something? That's oxygen. Okay. What am I going to get? Oh, okay. And the delta H of that, I could put that in my calorimeter. I could measure it. Because that's not a crazy reaction, right? That's pretty straightforward. Burn a little bit of coal. Okay. And we get negative 394 kilojoules. Right? Per mole. And this reaction uses how many moles of carbon? 1. So do I need to multiply that number by anything? No. Okay, good. What about diamond? Can I burn a diamond?
You can.
Yeah. So this, let's imagine that you have more money than good sense. Here's a guy in a lab, and in the jar is liquid oxygen. Because to burn something, you need to provide it with lots of oxygen. You cool it way down. You cool it way down. And there's a diamond. Oh, there's a diamond. Yeah. Now that diamond probably costs like hundreds of dollars. What's it becoming right now? Reacting with oxygen, so it's becoming carbon dioxide. Good. Let me tell you, there are cheaper ways to make CO2. This would be one of them. But there we go. That's what it looks like when you burn a diamond. So, okay, so what's this reaction going to look like? And what's the energy difference in that case? Delta H is negative 396. And I'm not going to do per mole here. I'm going to multiply it by however many moles of diamond I have. How many moles of diamonds do I have? Kilojoules. How many moles? Just 1. So do I have to change the number? No. Okay, there we go. So here are the two reactions. They're very similar, by the way, aren't they? They're both endothermic? Exothermic? Which are they? Oh, I've got disagreement. Cage match. We'll set up a ring. You fight to the death. Winner gets the answer. Go. Okay, I think they're all bluff. Which is it? Exothermic. It's negative, which means that the enthalpy is decreasing. In other words, diamond has more energy in it than carbon dioxide. Makes sense, right? So when diamond becomes carbon dioxide, that energy has to go somewhere, and it goes into the air. So these both release heat. And pretty comparable, right? Now, here's my question. I want to know the delta H of this top reaction, right? But I can't do the top reaction. But there are two reactions here I could do. So bear with me. In the example of my race, we found her overall distance by taking her first run, right, from here to there, and then we added it to her second run. And as it happened, they worked out to 0. But what if she had run all the way down the hall, 20 meters, and then came back halfway? What would her total displacement have been? 10, right? You'd have done the positive 20, and then added to it the negative 10, and you'd have been left with 10. Does that make sense? So we can take her two reactions, her two movements, and combine them into one overall movement. We're going to do that with these reactions. I have two reactions, but we can algebraically combine them, because in the end, these are thermochemical equations. Can we mathematically manipulate an equation? We can. So let's take a look. The equation I want, my target equation, is really simple here, isn't it? What's on the left side? Graphite. What's on the right side? Diamond. Anything else? No, some heat, but we'll worry about that when we come to it. We have graphite becoming diamond. So with these two reactions, there's more going on. I see oxygen, I see carbon dioxide, but let's just look at the things I want in my target. If we call this first one reaction A, which species from the question is in that reaction A? Okay. And in the reaction I want, that graphite is on the left. And in the equation I'm going to use, in equation A, it's on the left. Okay. In the equation I want, I use 1 mole of carbon, graphite. In equation A, I use 1 mole. It's perfect, right? Do I need to change anything about it? So we're just going to write equation A out exactly how it is. We're going to say graphite reacts with oxygen to give us CO2. And I'm going to say the delta H. If you wanted to write the delta H in the equation, you know, like if you plugged in with on the reactants of the product side here. Products, because it's released, right? It's heat released. Okay, we'll get those. We're going to keep asking that question until we get it. Now let's look at the second one. It has diamond. Equation B has diamond on the left, but the target equation has diamond on the right. What do I do? Yeah, I'm going to reverse the reaction. So now we're going to say the reverse of B would give me what? CO2 reacts to form oxygen and diamond. Now, that we flip the reaction, what's going to happen to the delta H? If the reaction of diamond becoming carbon dioxide released energy, then carbon dioxide becoming diamond would have to? Good. So now the delta H will be what? It'll be positive 396 kilojoules. Good job. Does that make sense? If we, and it says very slow, if we reverse the reaction, then we also have to reverse the delta H, which means we just change the, did the number change? Nope. But the sign changed. Now what we're going to do with these two equations, add them together. This is going to add them together. What's that going to look like? Don't worry about canceling it. We'll get there. If I add these equations together, what's going to be on the left side? Is that true? That's okay. Okay. So we're gonna have the graphite, and we're also gonna have CO2, and then we're also gonna have the CO2. Everything from the left of both equations goes on the left. What about the right? Everything from the right is going to go on. So what is that? Yeah, carbon dioxide plus CO2 plus diamond. Now, McGowan, you were keen to point what out? What can we cancel? Carbon? No, because that's graphite, that's diamond. They're different. CO2. CO2. That's CO2 on both sides. And O2. If something's in a reaction and not involved in the reaction, we call the spectator. Doesn't matter. It can be removed. So algebraically, the oxygen and the carbon dioxide don't affect this reaction. What are we left with? We're left with graphite becoming diamond. Now, if we added the equations together, what should we do with the delta H? So delta H equals what? What was the first delta H? Yeah, and the second one was? Sure. And when we do that, what do we get? 2 kilojoules. Making a diamond, which requires incredible amounts of energy and pressure and time, when all is said and done, what is its net energy? 2 kilojoules. Yeah, not a lot of change. It absorbs some of that energy. A lot of it is released. You have to put heat in, but then during the course of the reaction, it will also put out a lot of heat. And so when all is said and done, even though it takes a lot of energy and pressure, the change is only 2 kilojoules. Not that different. Not that different. Now, is that heat absorbed or is that heat released?
Absorbed.
Good, because it's positive. Good. If we were to put it into this equation, which side would it go on? Left side, because it's heat absorbed. Good. Does this make sense? So the basic thing we did was we looked at our target reaction, and the first thing we looked at was graphite, because it's the first thing listed. And I went down to the 2 equations we're using to make this, and I said, does one of these equations have graphite? Only one of them did, the first one. So I said, is it on the correct side, or do I have to flip the reaction? In this case, I want graphite on the left, and it's on the left, so I leave it alone. I just write it again beneath. The second one I need is the diamond. So I look, and that is indeed in the second reaction. And then I ask myself, is it on the correct side? And in this case, I said, no, I want it to be on the right. It's on the left, so I have to flip the reaction. When I flip the reaction, I need to remember to change the enthalpy. Do I change the number? No. Just the sign. Good. You guys are going to try the same thing with this reaction. Next page, same exact question. You're going to find the change in enthalpy for nitrogen gas reacting with oxygen gas to make nitrogen dioxide using the 2 equations below. All right, and this, just go through and do it. If you get stuck, then all of the same, that's a little puzzle. You got to figure it out.
Yeah, I'm not. Oh, yeah. Oh.
How are you doing? Dan? Because if we reverse this reaction, O2 is going to be the same size.
You're looking for equation 2 of 6.
I don't know this stuff. I know these 2. Let's start on the left. N2. You find N2 and I.
Oh, I see.
Here it's on the left. Right up reaction now. Just how it is. What? It's the whole thing. That's how it is.
You'll make it equals
Good. And then write the number next.
minus plus negative 1.
Cool. Okay, now it's O2 equals. Is it these reactions? Oh, it's in both. Let's I don't know what. What about NO2? Is it in the other one as well? Good. Okay, so this is just these. Good. Yeah, switching, not just it, you have to flip
Talk to each other, by the way. Keep it out. The equation. Just take this one. Just flip it.
What the fuck?
Oh, yeah, okay.
Oh, that's why. Mofo.
Oh, I get the chair on bearings. And remember,
Oh, make it negative.
yes, we make it negative because we switched it. Now, switch around. Hopefully, people don't figure it out. I can't tell you, but look, energy is on these. And you want it to be on these.
Delta H is 68 kilojoules.
That's what happened. You want it on these, you get it.
Oh my god.
But you know what you do? People,
What? No, I was saying, oh my god, because I dropped an F-bomb while I was writing my answer. I was like, what? Two. 3? No, you said 2.
I don't know.
Oh, man. Yo, just look at this. I just copied this.
Neat. Hi, come on in. Come on in, don't be shy. Wow. Wow.
Oh, no. No.
Okay.
You're to write the answer. No.
Yeah, the answer?
No. Here's the answer?
I love what you did here, but you didn't switch the side on that delta H.
Okay. So they're subtracted?
Yep, so the only thing is that should never be negative. Right? Another one?
Right. There you go. It's recording.
Okay.
Is this music right now?
Here's the deal.
Wow.
Yeah.
Yes, that's nice. Does it like make it nice? Oh yeah, it does. What? Like it makes it smooth. Yeah.
So I mean, that's really progressive at the end of the day.
It's Wednesday today.
It's due tomorrow, but you basically have to do it today, or else I'm gonna get really mad. Because you guys still have to pin in baby pictures too. Well, after the grad quotes, nobody's handing in their grad quotes, so it's kind of getting a little insane. And you know when the yearbooks due? Last Monday. Yeah. That's dumb. Why would you? No, everyone in this lesson can hear your answer.
Okay, guys, how we doing with this? Okay. Yeah. You're killing me. Oh,
I'm good.
I tried to open it next door once and I opened it like 11 times, which is a lot. What's that reference to? Anyone? Local Ring Scholarship of the Ring, specifically at the beginning. And yeah, and It is 11 uses. Ooh, I like half of you. I like, that's what I like. All of you half as much as I can only get four. One is the back end. Yes.
So could you just reverse one of the, like, couldn't you just reverse one of the delta H's in the top?
That's
Like,
exactly
once
what
you
it is.
figure out what equation you have to.
Just, yes, what I want to caution you is you always want to check and make sure that they actually cancel everything on one term or add the other one. In this case, for example, then it doesn't. It's only true if you end up with the exact same reaction. So in this case, we need to be sure that the nitrogen monoxide goes away.
Yeah.
Right? If it doesn't cancel out, then we're not getting a return reaction. We need to make sure that the oxygens end up on the same side so that we get two. If you can eyeball all that, great. And like one of those things, you get the right answer, you'll get the marks. But there's nothing saying I can't put a question on there that doesn't work. In fact, let me just make a guarantee right now. You're going to come across questions where the trick is that you can't get there from the target. And then you say, I can't find delta H. So it only works if we end up with the target reaction identical. That's a great question. In this case, we do, so now we can add delta H's. Making sure we remember that we flip that to negative, which we did. And so we should get what is our answer? 68? Okay.
Ooh.
Sure, 180 plus negative 112 should be 68. You like this so much. It's actually really awkward just watching the numbers appear without seeing like your hand right on time. I mean, we had the opportunity to watch. Maybe we do this.
Thank you.
Lots of practice. All right, let's go on. Let's go. Okay, let's look at the next example. We'll get there. All right, next example I have titled. That's awesome. Okay, so we've got three reactions now. Oh, that's going to be complicated. Let's just start going. Let's start with the target reaction. What's the first thing we see in the actual reaction we want to make? 4C. Carbon. Okay, how many of them? 4. Okay. And on which side? Okay, let's look at our three reactions, A, B, and C. Does any of them have carbon?
Yeah.
Which one?
A and B.
A and B. Where is A?
Sorry.
I see carbon in A. Am I wrong?
Well, it's carbon and C4.
Okay, no, but I mean carbon by itself. Same thing as in the reaction. If you look at the reaction, it's solid carbon, right? Well, I'm going to start with the reaction at top. I want that. Just that's how I like to work. So what I want is to work with ones that only appear in one reaction. And carbon fits the bill, right? It appears only in the second reaction. Do I have to reverse the reaction? No, carbon's on the left in my target reaction, and it's on the left in reaction B. But what do you notice about them that is different? Yeah, how many carbons do I need? How many do I have? What can I do with this reaction? By? Good. So down here, we're going to start with reaction B. We're going to say 4 times reaction B. And what's that going to give me? 4 carbons. Okay, good. Okay, and the delta H will be what? Oh, come on, 1600 minus 4 times 7 is 28. So that should be 1572-ish? 1574? Ah, wasn't fast enough. Okay, and negative or positive? Yeah, you can tell it's going to be even because 0.5 times 4 is 2.0. So anyway, I got made on Twitter. Is what I'm going to tell myself to make myself feel better. Okay, good. So we've taken care of the carbon. Now let's look at H2. Does H2 appear in any of these? Does it appear in more than one of them? Good, then I like it. I only want to use it if it only appears in one place. So it's in C. How many do I have here? How many do I have here? Oh, I hate my life. What am I going to have to multiply this by? Yeah, by 5 over 2. Ew. Ew, I don't like that at all. But that's what it is. Okay, so let's go. What's 5 over 2 times 2? Good. So 5 hydrogen gases. Good. Plus 5 over 2 oxygen. Yields 5 waters. Okay. And what's the delta H for this guy? What? Negative. Am I going to do it in the example lesson? Yes. Do you have to be careful? Yes, because, for example, here we have water as a gas. Gas, gaseous water, and liquid water, not the same. So you have to be careful. If you trust yourself to not make a mistake, go nuts. But you do have to be careful because gaseous water and liquid water have different enthalpies, right? If you look at the first example, the whole thing was based on carbon graphite and carbon diamond, right? So if you just treated them both as carbon, you wouldn't have gotten an answer. You do have to carry them. Will you sometimes choose to live on the edge and not? Of course. But, okay, now let's look at the last thing we need. C4H10. Does that appear somewhere in our reaction? Yeah. Which one? A. No, is it on the right side? So we're going to have to reverse it. What about the number of them? Good, so it's just going to be reversed, but not changed. So when I do that, what do I get? 4CO2 plus 5H2O yields C4H10. That appears to be H110. That's different. Okay, and then plus what? Okay, perfect. I'm going to throw things at you. Heavy things. I'm going to be trying to hurt you. Okay, and then what do I do with that number? Delta H now is going to be, okay, 2,000. No, Ms. Burns, I'm going to hit him real good. They're going to be on my side. Okay, so now I'm just going to add these things up. And I'm going to cancel kind of this way. I have 5 H2Os on the left here, right? Do I have 5 H2Os on the right somewhere? I'm going to cancel that. Yep. Yes, yeah, I should have said that. It's simply not said because I forgot to put it in when I wrote the question. Not lazy, forgetful. I'm often lazy. This is not a case of that. Though there will be cases. Okay, let's keep going here. I have 4 carbons. Can I cancel that on the right? I don't think so. Okay. It is. Okay, finish this one. Make sure it works. Then there's talking. So give me this 36 and a quarter seconds once this ends. Okay, I'll be done really quick, I promise. Finish this question. There's also a series of homework questions for Hess's Law. Go through them. There won't be a lesson tomorrow, but we're going to do some work. Lots of work. We're going to be productive. On the Tuesday or Wednesday that we're back, you're going to do a lab on Hess's Law. It's a calorimetry lab. This is going to be a formal write-up. So prep it into your book, but you don't need to do a wild prep into your book, because in the end, your book is just going to be to collect data. The presentation to me is going to come in the form of a formal report, all right? So I don't relax. So I don't need, listen, you have to write one of them. I have to edit 48 of them. I don't want to hear it.
For the Hess's Law?
Yeah.
You want it in our lab?
I want you to prep it in your lab book enough that you know what you're doing and to collect your data, nothing more than that. Your lab book's going to be for data collection, that's all, okay? Probably the Tuesday, maybe the Monday, I'll have that clarified by tomorrow, likely the Tuesday, okay? Can you give it to me today and I'll get back to you tomorrow? We're not doing a lab tomorrow.
I need to ask you a question and
Okay,
answer about it.
let's do that then. You're